Okay, so we were discussing robotics. Jeez. What the heck, man? Sorry. Okay, there we go. Sorry about that. So my computer is acting completely weird today. All right, so project management. Not just regular project management, we're going to discuss how to sort of do it in the context of a robotics project. Okay, so the first thing you need to do is the first step is break down the problem. Okay, so before I get into the details of this, just a couple of important caveats, right? Number one, everything I'm talking about is going to be very generic, so it's going to be very very general. So it might not apply to specific instances of your project, but it's supposed to encapsulate all types of robotics projects, right? I'm just basically going to talk about the big sort of components of a typical robotics project. So it's up to you to kind of adapt it to your specific project. The second caveat is that nothing I'm going to talk about in today's lesson is written in stone, right? So this is just how I approach a problem. That doesn't mean there's only one way to do it. It doesn't mean that you need to follow everything I'm saying exactly to the the nitty gritty details that I'm going to go into. It's just one way of approaching the problem, and it's completely up to you to approach it any way you like. But this is based on my experience, right? So let's talk about a typical robotics problem. So obviously, if you're talking about a typical robotics problem, you need the robot, right? So the first component. So if you're trying to breaking down this problem, the first component that you have to think about is the robot, right? So you would have a robot. This is my general idea of a robot, and this can be either in hardware, or it could be in simulation. Okay. I apologize if my writing is a bit weird because my computer is still acting slightly strange, but let's power through this, right? So it could either be in hardware or simulation, right? So the great thing about ROS is it doesn't really matter, right? So there might be slight variations between the hardware and the simulation. So some of the robots might not completely have all the sensors and things like that, but generally when you're talking about the final sort of topics that you'll be considering from a ROS perspective, it doesn't really matter whether it's hardware or simulation. Obviously, for you, you would obviously want to kind of play around with the hardware and actually interact with it. But other than that aspect of it, there's really no difference. I guess another small difference is the fact that you have to set up the simulation, right? And that might take some time in and of itself. But you come into a similar problem with hardware as well, which is kind of setting it up, right? So so the first problem that you have to deal with if you're breaking down the problems is the hardware setup, right? So if it's actual physical hardware, you'll have to go interact with the robot, set it up, get it working, power it up, see what it looks like, get a feel for it, right? If it's simulation, you have to do a similar step. I provided a PDF that helps you set up the simulations. But basically, that's the first problem, right, that you need to solve. Basically, set up the simulation or the physical hardware that you'll be working with. Okay. So this also, for example, if you're dealing with simulation, this also involves the environment, right? So it's not just the robot. So there's the robot. Plus, you need to have some sort of idea about the environment, right? So that it's going to play around with, right? So if it's a simulation, you'll have to look at okay, if you're dealing with a turtlebot simulation, what sort of different simulated environments can I look at, and things like that, right? So you get a feel for it. And then if you're actually working with physical hardware, again, you'd have to think about what sort of physical space will it be operating in, right? What sort of limitations will I be dealing with in that aspect, right? So all of that comes under this setup of the robot and the robot and its environment, right? So that's the first problem that you have to kind of deal with. Second, right, is basically you need to get information out of the robot, right? You need to get information out of the robot. So get info out of the robot, right? So that's going to be your second problem, right? So again, Ross makes this pretty easy. You can do this using subscribers. You can listen, right? Listen to the topics that you want to. You have to look at what sort of information is this robot publishing, right? And you can use subscribers to get information out of the robot, right? Which is the second big problem that you have to kind of solve, right? Once you set up the simulation, once you set up your hardware, look at what sort of information is being given out by the robot's sensors, right? And try and get that information out of the robot. First, you would try to do that using the terminal, or then you try to do that using MATLAB or whatever software that you'll be using to kind of do everything, right? And once you get this information out, and this is sort of the big chunk of where you'd be spending a lot of your time, it will be basically processing that information, right? Processing information, right? So once you get the information out of the robot, you have to process that information. So when I'm talking about processing information, there are two aspects to this, right? First, you need to what do you call it, sort of extract features, or sort of first you have to process the sensor information, right? Or let's call it processing sensor information. And then once you process the sensor information, you have to make decisions, right? So make decisions, right? So once you process the sensor information, you have to make decisions, and instead of calling this processing info, I just call that just processing, right? So there's two aspects to the whole processing. One is decision making and processing the sensor information, right? So this is where you'll be spending most of your time, right? This is the big problem that you have to solve. Basically, once you get this information out of the robot, you'll have to process that sensor information. For example, you'll have to identify features, right? Figure out, for example, some of you are grasping a can, right? Like, how do you recognize the can, or how do you recognize an object? Or if you're working with a project where it's two turtle bots following each other, based on a QR code or something like that, like how do you identify the QR code? That is processing the sensor information that you just got out of the robot. Once you do that, you have to kind of decide, okay, once I process that information, how am I going to, what should I do with it, right? And that's the decision making process, right? Once you make that decision, right, you need to get the robot to do stuff, right? So I'm gonna call that get the robot to do stuff that you want to do, right? So that will be, I'm going to call that the third problem, right? What I mean by that is basically, once you make a decision, let's take a simple example. If it's one robot following another robot, you got the information from a camera, right? You identified the second robot that you're trying to follow. You made a decision, okay, I need to move forward. And then now you have to transfer that information to back to the robot, saying, okay, I want the robot to actually move forward, for example, right? And this can be done using a publisher, right? So this is assuming you'll be using ROS, right? So for you to get information back to the robot and tell the robot to do stuff, that's where you use ROS publishers, right? So the reason I called I didn't call this big block in the middle number 3 and I looked at this as number 3 is because the whole idea here is that you want to do all of these in a modular way, right? You want to first set up the robot and its environment separate to any of the things that you're doing here, right? So getting the information out of the robot, for example, has nothing to do with how you're going to process that information. Even, for example, getting the robot to do stuff you can do that independently of actually the decision that you make, right? So what I mean by that is, even before doing this big red block here, see if you can publish information back into your simulation, right? So you can hard code values. For example, if you can tell the robot, okay, move forward, right? Move forward 5 meters or something like that, right? And then hard code that value, see if you can publish that back into your simulation, back into your robot, and get it to move 5 meters forward, right? So that has nothing to do with this block in the middle. So try to do all of these as separate, independent modules, right? So I'm just going to put these in squares to kind of emphasize the fact that these are like separate modules, right? The advantage of kind of breaking it down into these separate modules is you bite off only one chunk of the problem at a time, right? Without approaching all of it at the same time, which can be quite difficult, right? So getting the robot to do stuff, you publish some sort of hard-coded values and see if you can move the robot. For example, if it's a robot arm, see if you can move the robot arm into places that you want it to move, right? So that once you decide where to move, you can just use that same pipeline that you just created to do it, right? So these modules 1, 2, and 3 is what you would do first, right? You would try to get set up the simulation, get information out of the simulation, and see if you can publish information back to the simulation, right? Or the hardware. Okay, so these first 3 are basically what you have to do really quickly and get that out of the way as quickly as possible, right? And these 3 parts will generally be the easiest part of your project, right? But remember, the bulk of your project will be spent in this part, right? Basically, how you're going to process that sense information, and once you process that sense information, how do you make decisions based off of that sense information? That is whether to move forward, whether to move backwards, whether to move the arm forward to the side or whatever, right? So that once you made that decision, all you have to do is just connect it to this module, and since you've already figured out this module, everything will work smoothly, right? So that's kind of the hope, right? So this part is where you will be focusing on a lot in your project, and give yourself enough time to do this part, right? Because that's where your contribution is. But these other sub modules 1, 2, and 3, you need to get out of the way as soon as possible, right? So get that done like this week. Just see if you can get information out and process it, right? So to kind of help you get information out, you can use okay, so before moving there, right, let's talk a little bit about this block number 4, right? Processing sense information and making decisions. So there's multiple ways you can approach this. You can do this in MATLAB, right? You can do this in C++ or Python, right? You can basically either way you'll be using ROS, right? So if you're using MATLAB, for example, when you're subscribing into information and listening to information coming from the robot, you'll have to kind of get that information to MATLAB, right? So there's a small sub problem associated here. I'm just going to call it 2.5, which is connecting to MATLAB, right? Connecting ROS to MATLAB. And similarly in here as well, right? You have the same problem, right? But once you connect everything to MATLAB, it's kind of two sides of the same coin, right? Once you connect everything to MATLAB, you can then publish back into ROS or subscribe from ROS, right? So connecting to MATLAB helps you get information out of the robot so that you can do this processing part, right? So that you can load it onto MATLAB and then kind of process it. Again, you don't have to do that. You can use C++ or Python if you want to, but since most of what we've been doing in these tutorials are MATLAB, there's nothing wrong with using MATLAB to do this as well, right? So for most of your projects, MATLAB will be the easiest way to do this, because if not, there's an additional learning curve to deal with when you're dealing with C++ or Python, right? Because you have to kind of learn the basics of that as well. But since you kind of invested your time in MATLAB right now, there's nothing wrong with dealing with MATLAB. And since you're here to learn robotics and not to learn a programming language, I even urge you to consider using MATLAB, because you can visualize things very easily, you can debug things very easily, and it'll be slightly slower than C++ or Python, but trust me, you have only 5 to 6 weeks, so go with the easy option right now. Okay, so just a couple of important terminology, right? So getting information out of the robot and processing that sensor information. Use a different color. Yeah. So this bit that I've drawn in blue, right? This is what we call the perception problem in robotics, right? So you're trying to perceive things coming from sensor information, right? So you first need to extract that sensor information, get that information out of the robot, and then process that sensor information so you can kind of extract features and things like that, right? So everything that we did so far in our class, right, come under this perception problem, right? So everything that we discussed in sensors so far, right, about cameras, about LiDARs, all of that come under here, right? And we talked about different ways we can extract features, right? We talked about SIFT, right? We talked about Harris corner detectors, right? Convolution, all that stuff come under this section, right? Which is basically, once you get the information, how do you process that sensor information to kind of get the things that you want to look at in your application, right? Then you have the decision making part, and once you make the decisions and kind of, the part where you're trying to get the robot to do things, right? So that's where the control aspect of this comes into play, right? So once you made the decisions and you want to get the robot to do stuff, that's where the control aspect comes. And so when you're talking about control, so we haven't really looked at control much yet in the course, but you don't have to worry too much, because most of the robots that you'll be working with, for example, the Turtlebot, the Fetch, right, most of them come with control packages already pre-installed, right? So for example, let's say you want to move 5 meters, you don't have to design a controller from scratch, right? Because the Turtlebot and Fetch packages already have easy to use control packages inbuilt, right? But that doesn't mean that you always have to use them. For example, if you want to, you can design your own controller from scratch. And I think some of the projects that's mandatory. Like for example, I think there is one project where you're supposed to control a handheld RGBD camera or something like that, right? So in situations like that, basically the control aspect is it's important that you build it from scratch in projects like that, right? But identify what your main target in your project is in terms of control, right? So for example, you can use these packages like MoveIt and so on to easily control your robot. For example, all you'll have to do in some cases would say move 5 meters, and it will move 5 meters, and it will do all the complicated controlling bits underneath the hood, right? But what's great about most of these packages is that if you want to implement it with like from scratch, you can still do that as well, right? So you have access to, for example, if it's a robotic arm in the Fetch robot, you have access to all the joints in the robot arm, for example. So if you want to go and create a low-level a controller that works from scratch and you want to design a controller, that option is also available to you. But in most cases, if you're dealing with the Turtlebot or the fetch, you can very easily just pass on commands and it will do them, right? But again, there's a small learning curve there, so try to, and that's this part, right? The number 3 block. Try to look into that as soon as possible and see what sort of options you have to actually control your robot, and try and implement them. Again, implement them in a modular way so they're disconnected from, like, you don't have to complete number 4 to go to number 3, right? You can do number 3 by just hard coding values and seeing what your robot does, right? So yeah, so you have the option of designing a controller yourself or using the controllers that come kind of inbuilt with most of these ROS packages, right? But generally, designing a controller from scratch is a very, very difficult thing to do. And if you have a unless that's your project itself, which is the case in I think 2 or 3 of the projects, I would suggest just using the inbuilt controllers, right? Because tuning them and designing them is generally quite a difficult task, and can be a project in and of itself, right? So the reason why we teach you the control section in this course is so that when you look at those controllers that other people have implemented, you can understand how they kind of work, and then you can tune them to kind of match your own application, or you can write your own controller from scratch if you know, if you have some free time and that's what you want to do, right? But yeah, so break down the problem like this. So what I was really looking in your proposals was like, what are the solutions you have for this part, right? Like the perception problem, like how are you going to detect like different features, like what are the features you need to detect, things like that, right? And then once you make the decision, the second part I was looking in your approaches were like, what are your control strategies, right? Are you going to implement a controller from scratch? Are you going to use the inbuilt kind of packages, or like what are your approaches? And some of you had answered those really well. Some of you had just not mentioned anything with regard to any of these problems, right? So before we move on, any questions regarding this, right? So the idea here is to kind of break down these into mini problems, and even this processing block, right? Even this processing block, you try to kind of break it down into a set of smaller problems, right? Break it down into a set of smaller problems, and before moving on to a problem, make sure each of the modules work kind of independently of each other. That way, it's easier to debug, and it's easier to move from one problem to the other, right? So see what you need to do first before you kind of start doing it, and then break it down and plan it out and go step by step. Okay, so any questions so far? Is this clear? Like, again, none of this is written in stone, but this is a typical kind of loop when it comes to a typical robotics project, right? Okay, so again, 1, 2, and 3, do it as quickly as possible. Complete it as soon as possible. That's the easy part. The fourth component is going to be what's going to take most of your time. So once you break down the problem, second thing is figure out your timeline, right? Which is going to be super important, right? So take each of these sub problems and allocate which week. Look at how much time you have and kind of allocate each of these tasks to a specific date, and have a deadline for each of these tasks. Because if you don't set a timeline for yourself, it's going to be like time is going to kind of slip away from you. Okay, I have a question. Should we set it so using launch files or just ROS run? Also, should we use Alvis instead of Gazebo? Okay, so I mean, you can create a launch file, so there's nothing like specifically launch file would just make it easier, right? But it's not that we're going to mark you down because you didn't have a launch file or something like that, right? So as long as your final demonstration works well, that's all that matters, because at the end of the next 5 to 6 weeks you have to do a small presentation and show everyone. It's like a 4-minute presentation, so you have to kind of demo your project. So what we're really looking at is the final demo, right? We do look at the code as well, but it's not essential that you create a launch file and things like that. But the launch file just makes it easier for you to kind of do your project. Also, could we use RViz instead of Gazebo? Okay, so RViz is not a simulation tool, right? So RViz is just a visualization tool. So RViz is good if you're kind of visualizing sensor information that's coming out of your robot, for example, right? But for it, you can't simulate things in RViz, right? So there's no physics in RViz. There is no you can't, for example, build say a wall, or all sorts of different things. Depends on your project, right? So if your project is like 2 turtlebots following each other, then you don't necessarily have to use Gazebo. You can do it in RViz. But for example, if it's a grasping situation where you're kind of trying to detect an object and grasp it, you will have to sort of use Gazebo. Again, I think because there's a perception element into this, because you have to kind of sense things and detect things, I think you'll have to use Gazebo, right? Because you need to generate information, right? For example, in your simulation, right? Let's say you have a robot with a camera, right? And then there's an object in front of the robot. So this camera has to actually get information from this object and create an image, right? Let's say of an object like this. So for that to happen, you have to simulate this object. You have to simulate this camera, right? And then this camera has to actually capture this information and create a camera image, right? It'll be a simulated camera image in the sense that the object is simulated, but from Ross's perspective, what it will be giving out is a camera image, right? It doesn't know whether this was a simulated object or not, but it's created a photograph of that object as if that object was actually there. So to do that, you need a simulation of that object in front of the camera, right? And you can't really do that in RViz, right? RViz can show you this part, right? So once you take the image, you can visualize that image in RViz, for example, but it can't simulate a fake object where you can then simulate a camera and detect that object, right? So the reason Gazebo uses so many resources is it's simulating the sensor itself, it's simulating this fake object, and then generating that image, right? But if you want to visualize that image, then you can use RViz. I hope that makes sense, right? So all the simulation bit has to be handled by Gazebo. So how powerful should the GPU be? I mean, you should have a decent enough one. Like obviously you don't need to have a high-end like RTX like 2080 or the new 3000 series or whatever, but like a generally decent GPU would do the job. Obviously you can't get you'll have to spend a lot of money on something like that, but I think like a general laptop that that can run Windows without any lag should be enough for the Gazebo simulation. There might be a bit of lag, it might be a bit slow, but you'll have to deal with it. So that's why at the start of the course I also mentioned that dual booting might be a bad idea and things like that, because it just makes it additionally slow on top of everything else. But yeah, unfortunately this is a issue when we're having to deal with simulations, right? And it's not an issue we generally face in our course because usually we work on practical hardware, but since last semester, unfortunately it's a bit of a problem. So if you're working in a group, maybe let the simulation be run on someone's computer who can actually handle it. So another thing you can do is you can simulate everything in Gazebo and then record a ROSBAG, right? You record a ROSBAG. So for example, if you're dealing with this perception problem, right? If you're just dealing with getting information from the robot and processing the sense information, you can just record a ROSBAG in Gazebo, right? And then you don't have to run Gazebo after that. You can just play the ROSBAG and then process that information, and then you can develop your algorithms. Right? You can develop this part of your problem. This part of your problem, right? Everyone can see my cursor, right? You guys can see my cursor, right? Okay, cool. Yeah, so for example, in this part, you don't always have to run your Gazebo simulation. You can because it'll be annoying. I get it. Like especially when you're debugging code, you'll have to make mistakes, rerun the code over and over again. So in a situation like that, use ROSBAGs, right? Obviously, when you're doing this part of the problem, though, when you're dealing with the control part, you will kind of need your simulation running because you need to publish information, and you can't kind of do that on recorded data because you kind of need to control things and change things. So in that case, you can't use a ROSBAG. But for this half of the problem, you can use a ROSBAG, right? Actually, up until this making decision part, you can use a ROSBAG, which will make debugging your code very easy. But then when you're actually publishing information back, you need your simulation because you want to kind of inflict change on the simulation. All right, so I hope that answers your question. So back to what we were talking about. So yeah, just make sure you allocate everything in your timeline, each of these different components. One important thing when you're making the timeline is be aware of what you call the planning fallacy, right? Planning fallacy, which is basically humans tend to underestimate how much time it's going to take. So for example, if this has been seen in a lot of government infrastructure projects, like whenever there's like a new highway that needs to be built or something like that, it usually takes several months or sometimes even years more than what was originally planned, right? And way more money than it was originally planned, right? So humans tend to kind of underestimate how much time it takes. So give yourself plenty of time, right? Make sure you start now. Don't waste your time, especially because each of these parts, right? This part, each of these parts are going to be frustrating. It's going to be difficult because it's the first time you're doing this, right? You never set up a simulation before, unless you have, but most of you probably haven't, right? So there is a small learning curve to each of these sections, right? So trust me, like even at this point in my experience, like there's all like dealing with open source software, dealing with robots, things will always go wrong, right? So it's like what we generally refer to it as Murphy's law, right? Whatever can go wrong will go wrong always, right? So when you're dealing with these kind of things, just give yourself enough time. Expect to be frustrated, right? Even the most experienced people will still get frustrated when you're dealing with it. Like your code might not work, you don't know why, and then you'll have to spend like a whole night trying to debug your code. Like it's part of the process, right? So don't feel like you're stupider than everyone else or anything like that. Everyone goes through it. Like everyone I know who's doing PhDs and who's like my experience during undergrad, like whenever you're dealing with a project, expect things to go wrong, expect things to be difficult, and understand that there is a learning curve associated with each of these sub problems that I pointed out, right? Even something as simple as setting up the simulation. So most of you, I think, have already started on that and you've already run into quite a few problems, right? So one of the skills you will be learning is the skill to debug, right? Whenever something goes wrong, like that's a skill in and of itself, how to kind of debug problems and figure out solutions, right? So obviously you can always ask me, but I'm also really busy, so sometimes I might take a while for me to reply to your emails. So learn how to debug your code online, like how to look through forums, read through documentation, and try to solve problems. And it's this process of debugging, that's where you learn. That's where you kind of learn how to, like even Ross, right? obviously you can watch a couple of tutorials, but until you actually implement these sections and run into problems and find the solutions to those problems, I don't think you can learn Rust by just looking at a few YouTube videos or reading about it, right? So robotics is a very practical, skill based thing, right? So the only way you can really gain that experience is jumping right into it and doing it, right? And I think a lot of people face the problem of feeling like you're too dumb, or like, especially when you get stuck on a problem and everything looks really complicated, you might not understand the code that other people have written and things like that, and then you think, okay, I'm really stupid, like why am I like this, like you feel really low, and that doesn't help, right? The important thing you need to realize is everyone goes through this problem, especially when they are learning something new, right? And this course has a lot of things that are new to a lot of you, so it will challenge you. The only thing you can do to help yourself is give yourself enough time, right? And which is why I said, even the first couple of weeks when you started this course, make sure you learn MATLAB, right? Make sure you learn ROS, right? The basics of those things, so that by the time you start the project, you don't have to worry about the basics. You can start worrying about more complicated problems. Now, if you haven't done that, and in week 6 you're suddenly trying to learn MATLAB and suddenly trying to learn ROS in a deeper way, you're in a bit of, I mean, it makes your already difficult task much more difficult, right? But again, right now we are in week 6, you still have time, so I mean, you can still spend some time learning those things. But the every day that goes by, time is getting, like, you're losing time, right? So don't waste time. Make sure your timeline doesn't fall into the planning fallacy. Make sure you give yourself enough time. Overestimate the amount of time that you'll be taking for each of the sections. And that's where the third component in project management is important, which is teamwork, right? So most of your groups have like 2 to 3 people in it, so make sure you delegate tasks, right? And it's not just important that you delegate tasks. The people who get delegated those tasks need to pull in their weight, right? Because ultimately you're going to be scored together. Like, we'll be looking at your individual contribution, but ultimately your final demonstration is what's going to give us the perception of your entire project, right? So like, obviously we will be looking into your individual contributions, because the final report has to be an individual report. But if not, like, if people don't pull in their weight, it's going to bring down the whole group, right? So teamwork cuts both ways. You need to, obviously, if you're the lead of the group, you need to delegate tasks. Don't try to do everything yourself, because that's impossible. And on the flip side, the people who get delegated tasks, you need to contribute, right? And if you're stuck and if it's taking too long, get help from your teammates, right? And say, okay, this problem is quite difficult, I'm stuck. Don't let it fester, right? Like, for example, in this timeline, if you are supposed to finish a certain task in 1 week, right, and by the end of that week, like, you've faced a lot of problems and it's just not working, address it as soon as possible. Get your teammates involved. Like, communication is also important here when you're talking about your teamwork. Talk to your teammates. Say, okay, this is a potential problem we're gonna have. I've tried my best this whole week. It hasn't worked out. What are our options now? Like, what can we do? Maybe you can get someone else to look at the problem, right? Or you can contact me and then we can, like, solve the problem. Don't wait, because what's going to happen is the weeks will go by really fast, and then ultimately you just have 1 week left, and then you just be stressed out, you'll be depressed, right? And you don't have enough time to finish everything, and then it's just going to be like, I'm telling you all this because I've seen it happen over and over again every semester, right? And it's like, usually the groups that do well are not necessarily always the smartest groups. It's the groups that started early and stuck to this timeline, and made sure that they do the amount of work necessary every week, right? And I know it's really difficult right now, and that basically brings me down to my fourth point, which is basically stick to the plan, right? I know that's quite obvious, but I think it's important to talk about it a little bit, because right now, especially with like the quarantine and like all the crazy stuff that's happening in the world. Like it's it's a quite a like psychologically depressing time, right? Like you open up any social media app, you're like hit with all this like the world is like falling apart. And like I know how difficult it is, especially to stay focused, stick to a plan, and do all of that, especially because like time itself is like really fluid and weird right now. Like um like the day goes by so fast. You wake up in the morning and next minute like the day is gone. But then when you like look back to last week feels like a month ago. So it's like your sense of time is all screwed up. You're stuck at home. Like things, I get how difficult things are for most of you. So use this project as a way to kind of help you get out of it, if anything, because ultimately, like you know ultimately by the end of the next 6 weeks, you will be designing a fully functioning robot, right? And that itself is really cool, right? So try and realize how cool that is, like what an achievement that's going to be by the end of this course, and give yourself that motivation required to kind of stick to the plan, because you can end this semester on a high note and feel good about yourself, that at least that you did your best, right? And right now that feeling of like little accomplishments matter, especially during this like really turbulent time, right? Some sort of win right now helps you psychologically, right? So maybe reduce your interaction in social media a little, focus more on your work, and at least that's worked for me a lot. Like putting yourself and focusing on these little problems helps you deal with what's going on outside of all of this, right? So yeah, just make sure you stick to the plan, and try not to lose that sense of urgency and sense of kind of focus during this time, because you let 1 week slip by, especially at this moment, since you have about like 5 to 6 weeks, things will become more and more difficult, right? So I'm here to help. Just email me anytime, and I'll set up a meeting after class so that we can discuss whatever issues that you're having in the project. But try your best to make progress every week towards your final goal, right? And the advantage of kind of breaking it down into these sub problems is that you don't have to deal with all of this at the same time, right? So, for example, when you're thinking about the simulation setup, you can forget about like processing the information and things like that for a bit, and just focus on this problem, right? That way, like otherwise, what happens is if you look at the whole problem as a whole, it becomes very daunting, and if you're trying to solve everything at the same time, it becomes quite difficult to debug problems, right? So try your best to break it down into these like sub problems. Like even each of these blocks will have sub problems inside of them, right? So try and take that kind of modular approach to things, and trust in the process. Realize that it's going to be frustrating, it's going to be difficult, and be strong, and have a sense of perseverance, because that's how you learn. And by the end of it, like every semester, every group does. I mean, if like people your age finishes this project by the end of the semester, right? Like it's been happening for the last like couple of years, right? So you can do it. It's difficult, but you can do it. And yeah, the key important thing is give yourself enough time and stick to the plan, and make sure that there is enough teamwork. Okay, so that's really the end of my rant. If you guys have any questions regarding this, you can ask me now before we move forward. Any questions? Okay. Yeah, so good luck with your projects. Hope you guys will do well this time. We had quite a lot of groups do really well last semester, so I'm looking forward to seeing what you guys got. Okay. Yeah, let me